Start recording. We'll see if I can actually do something right today. Okay, so we've got, this is back to the bike problem from the quiz. We got a bike, we got a creek. All of you could go out and recreate this over your break. Though don't tell them that I told you to do it because I want to keep my job. You can find this situation somewhere in the world. Can you get across the creek? Well, if there's no ramp, if you're just riding straight off the edge, to get across a 2.3 meter creek, you need an initial velocity of 3.9. Can you lower the initial velocity needed by adding a ramp? So let's recreate the situation, but give you a ramp. I'm going to copy this whole picture, I'm going to paste this whole picture, and I'm going to put in a ramp. We'll make it a little like 15 degree ramp, 15.0 degree ramp. And what we want to know is how will that change your initial velocity that's required? The overall initial velocity. So I'll shrink all of that to a tiny little speck in the corner where we can pull it back up if we need to. And this is now what we're working with. So what do we want to know? Well, we want the initial velocity. So I'm going to start the way I always start these, with an x and a y axis list of variables. I know that I need my delta x. What I'm interested in is the VI required to get me 2.3 meters after a fall of 1.75 meters. Change in, I should say, change in y position. Because we acknowledged when we started talking about this yesterday before I led you down a blind alley, that you're actually going to go up further in the air than you would if you just drove straight off. So we don't know what our max delta y is. We'll get to that. But we know that overall we're going to land 1.75 meters below where we started. So we don't know VI, but we do know that whatever it is, VIX, because there's our VI, VIX will be equal to VI times the cosine of the angle on our ramp. And again, VI is what we'd like to know. That kind of bridges the axes. But we know whatever VI is, VIY is going to be that initial velocity times the sine of our angle. And the angle is given by the ramp. We got a 15 degree ramp. Little teeny ramp, nothing big. What else do we know? A sub x is 0, a sub y, negative g, which is negative 9.81 meters per second squared. Why do I persist in writing negative g? Just to remind you, because it'll come in handy later. Okay, we're going to use the same equation that we've been using to get an expression for our bridge, because our bridge, of course, is time. And on the x-axis, because of the fact that velocity is constant, we know that delta x equals VIX delta t. So delta t equals delta x over VIX. I'm just going to pop that expression right into my variables list. And I used to, sometimes I would do that. I would circle the time so we know that that's the bridge. Well, I'm still working with VI, delta y, a, and delta t, so this is still a good candidate for my favorite expression. Delta y equals VIY delta t plus 1/2 a delta t squared, with all the substitutions that we know we can do. So I know that I can do delta y equals VI sine theta times delta x over VI cosine theta. And I know that that's going to be plus 1/2 a delta x squared over vi squared cosine squared theta. Now, I'm looking for vi, so I'm going to just do the little trick here of circling vi. And I want to ask you a question. Am I going to run into a quadratic solve again? I've got vi in two places. Nope, because my vi in the first instance is going to cancel out. So delta y equals vi sine theta delta x over vi cosine theta. I almost put another delta x in there. No. Plus a delta x squared over 2 vi squared cosine squared theta. I can cancel out those vi's. I can wave my magic trigonometry wand, which actually sounds like a lovely idea, a magic trigonometry wand. And once I do that, I have delta y equals tan theta delta x plus a delta x squared over 2 vi squared cosine squared theta. Now here we are going to have some relatively ugly algebra. And the reason we've been playing the mistake game is really these and the chapter 4 problems. Because you've got a lot of rearranging to do, and a lot of the classic places to screw up your algebra are contained in this problem. For one thing, the thing that you're solving for is in a denominator. Oh, you can totally do that, but it's also one of the most classic places to screw something up. So I want to just draw your attention to the pothole so you don't step into the pothole. The other thing is that it's part of an addition problem. There's a sum there. And if you remember, order of operations gets done in reverse order. When we're unpacking things, you have to undo the addition first. So I'm going to shrink this and undo the addition. So I have delta y minus tan theta delta x equals a delta x squared over 2 vi squared cosine squared theta. Not terrible. Because there's a lot to unpack here. Now in calculus, you start doing something called substitutions. You probably haven't done them yet, but it's a trick. Mr. Andres and I have talked about this, that it's a trick you don't get introduced to until calc, but it's useful in a situation like this. We've got complicated chunks here that we're solving. And so I tend to do this little mental trick for myself. Well, this whole thing, I'm going to call that A. And this whole thing, I'm going to call that B. And this whole thing, I'm going to call that C. And if it looked like this, could I get closer to isolating VI? Well, sure I could. Oops. Because if I look at it that way, then I know that AC equals B, and then I can start breaking stuff up again. People tend to, because this you have to treat as a single chunk, this is one of the places that people tend to screw up, is they'll attempt to divide part of that and not the whole thing. That is now an entire entity of its own, and it has to be treated as such. Hence my little substitution. Okay. So I also make heavy use of parentheses because it helps to remind me that that 2 vi squared cosine squared theta, if I was going to do anything with that and the y, delta y minus tan theta delta x, I would have to distribute that across both parts. That's a really common mistake that I see. So now I'm just about there. Does it look like I'm just about there? At this point, it's easy. 2 steps. You got 2 steps to sunlight. You can divide, so if we remember that VI is what we want, you can divide A delta x squared by every other thing over there. Easy peasy. So we have, okay, VI squared equals A delta x squared over 2 cosine squared theta times quantity delta y minus tan squared tan theta delta x. That's a mouthful. Guess what? Take a square root, plug in some numbers, and you're done. That was easy. Jeez. I'll just do that and then go ahead and plug in numbers. Do you see that these are some fairly heavy-duty rearrangements and they get more robust as we go? This is part of the reason that on tests I say, yes, you got to show your basic equations. Yes, you got to show the rearrangement. I give you credit for multiple points within this. I give you credit for that initial substitution. I give you credit for coming to the point where you've solved for your variable but haven't plugged anything in yet. So you're plugging in numbers frantically. I should do the same. No. I got 3.428 pocket change meters per second. It's a lot of work. They are. Is that lower than the velocity we needed with no ramp? Yeah, not by much. At that point, since you can make it without the ramp, I would say just ride that sucker. Okay, assigned all the practice in the book, and I'll have the worksheets for you. I'll have them tomorrow when you walk in. Some of you I know will be out, so you might want to pick them up. We're going to spend some time on this. This takes some time. And these are the easy permutations. Obviously, they get more challenging as you get into the worksheet, as you get into all that stuff. So get working on the book. Happy algebra. It is a great algebra review. It will strengthen your algebra muscles.